Take a close look at this rocky cliff in the Grand Canyon, and what do you find? Sloping layers of hard rock, piled one atop another. Smoothly rounded sand grains, all about the same size, cemented together. Animal footprints preserved in the rock. What do these clues reveal about the rock's origin? Dig a hole in a sand dune, and you'll find the answer. Sloping layers of sand piled one atop another. Smoothly rounded sand grains, all about the same size, shaped and sorted out by the wind. On the surface of the dune, lizard trails, small footprints. So this rocky cliff is actually part of an ancient sand dune that hardened into rock. The story of the rock's origin is preserved in the rock itself. We are able to read the story because we know how to interpret the clues. Let's use the same method to find out how some of the rocks here were made. The walls of the canyon are made up of various kinds of pebbles and boulders embedded in another rock. If we examine some of these boulders closely, we should be able to find out how they were made. Let's try it. This boulder is made up mostly of some dark material. Scattered through the dark material are many light-colored crystals. Does this tell us how the rock was made? No, not yet. Here is another kind of rock. It appears to be made of a light-colored material. A closer look shows it is made of light and dark crystals, all locked together. Again, the rock is a puzzle. Here is yet a third kind of rock. It is made of very small crystals arranged in layers. Again, the origin of the rock is a puzzle. To solve these puzzles, let's take a closer look at what the rocks are made of. The first step is to cut a slice from each of the three kinds of rock. The slices are cemented to glass slides and ground until they are paper thin. Now we have thin sections of each rock, so thin that light will go through them. When they are photographed with polarized light and enlarged, they look like this. And they show how the crystals in each rock are arranged. In the first rock, a few large crystals are surrounded by hundreds of very tiny ones. The second rock is made completely of large crystals that fit closely together. The crystals in the third rock also fit closely together, but they are small and arranged in layers. All three rocks have one thing in common. They all have crystals in them. But in each rock, the crystals are arranged in a different way. So, if we want to solve the puzzle of how these rocks were made, we must first find out what crystals are and how they are made. You may think that only things that look like this are crystals. Actually, most solid things on Earth are made of crystals. For example, sugar, metals, ice, and salt. Here's another crystal of salt, only bigger. It's easy to split or cleave the crystal again and again, parallel to one of its flat faces. If we try to cleave it in a direction not parallel to one of its faces, the crystal shatters. The fact that a crystal splits neatly only in certain directions shows that it is weaker in these directions than in others. But why? Here, magnified over 1,000,000 times, is what the inside of one kind of crystal looks like. The parallel lines are formed by many layers of atoms, the tiny particles of which all things are made. Now it is apparent why a crystal splits neatly only in some directions. It must split between layers of atoms. So crystals are made of invisible atoms arranged in regular patterns. The next thing to find out is how these regular patterns come about. These are crushed crystals of a substance called salol. Each crystal fragment is composed of millions of regularly arranged atoms. Watch what happens when we heat the crystals. The crystals melt. Heating the salol destroys the regular arrangement of atoms within the crystals, allowing the atoms to move about freely in the hot liquid. Now watch what happens when the molten salol cools. We'll use time-lapse photography to speed up the process. As the melt cools, crystals begin to grow in it. Millions of invisible atoms are joining together in regular patterns. The result is a mass of intergrown crystals. But why do atoms form regular patterns? This apparatus will help illustrate what happened. These plastic beads represent atoms. To represent heat, we'll use this vibrator. Now the model atoms are moving about freely, much as the real atoms in the melt must have been moving, although we couldn't see them. Now we'll slowly cool our model atoms by lowering the energy of the vibrator. As the model atoms lose some of their energy, they are slowed down and begin to pack themselves together. And because they can fit closely together in only one way, they form an orderly pattern. As the invisible atoms in the melt cooled and lost some of their heat energy, they formed regularly shaped crystals because they too can fit closely together in only one way. So atoms can form crystals only as long as they are free to move into regular patterns. What would happen if this movement were stopped suddenly? Let's find out. This crucible contains powdered bismuth borate crystals. When we heat the powdered crystals to 700 degrees centigrade, they melt. The atoms that made up the crystals are now moving about freely. When the melt is allowed to cool slowly over half an hour, it crystallizes. The result is a mass of intergrown crystals. Now let's repeat the experiment, but this time we'll cool the melt suddenly, in 30 seconds instead of 30 minutes. This time, no crystals form. By cooling the melt quickly, we froze the atoms in place before they could form orderly patterns. The result is a solid mass of unordered atoms. We call this glass. We can use the model atoms again to illustrate how the glass forms. Watch what happens when we suddenly stop vibrating them. The result is an unordered arrangement of model atoms, much like the real atoms in the glass. It is as though they were cooled suddenly, before they had a chance to group themselves into an orderly crystalline arrangement. So, to produce crystals, atoms must have freedom to move and time enough to arrange themselves into regular patterns. If this freedom is taken away, the atoms remain unordered and form glass. Now let's take the 3 sample rocks one at a time and see if we can figure out how they were made. The well-formed crystals in the first rock suggest that it was once molten. The fact that the crystals are small and separate suggests that the molten rock must have cooled quickly, becoming solid before the crystals could grow any larger. Where in nature is molten rock produced and then cooled quickly? Every time a volcano erupts, molten rock is thrown out onto the Earth's surface. As the molten rock loses its heat, it thickens rapidly. As a result, if any crystals were growing in the molten rock, their growth is slowed down or stopped altogether. Within hours, or at most a few days, the molten rock hardens. Molten rock that was thrown from a volcano before any crystals could grow in it may harden into a natural glass like this obsidian, a kind of volcanic rock. If the rock were cooled suddenly after crystals had already begun to grow in it, it may look like this. This, or this. All volcanic rocks. How was this second piece of rock formed? The crystals in it show that it was once molten. Because it is made of large crystals, completely grown together, we know the rock must have cooled slowly enough to give all the atoms in the rock time to form crystals. Where in nature is molten rock produced and then cooled very slowly? There is only one place where this could have happened, and that is deep underground beyond our direct observation. Volcanoes prove that temperatures deep in the earth are sometimes high enough to melt rock. When a mass of underground rock melts, the overlying blanket of sedimentary rocks and the remaining body of unmelted rock act as insulation. So very little heat can escape, and the pressure of the overlying rock keeps liquids and gases from boiling away. Over a period of thousands of years, the molten rock cools. As it cools, crystals grow in it, changing the molten rock into a solid mass of intergrown crystals. If forces acting within the earth should now push the crystalline rock upward, erosion would uncover the rock. The eventual result is a mountain range made of intergrown crystals. Rocks made in this way take many different forms. They are called plutonic rocks after Pluto, Greek god of the lower world. Because both plutonic and volcanic rocks were once molten, they are both called igneous rocks, after the Latin word for fire. So we are left with one unsolved puzzle. This rock is also made of intergrown crystals, but in this case, the crystals are arranged in distinct layers. This suggests that the rock never melted, at least not completely, because melting would have destroyed the layers. But if the rock didn't melt, how can we account for the intergrown crystals of which it is made? A demonstration with this wafer of steel will help answer that question. We'll put the steel wafer into this special microscope. The steel is heated to 850 degrees centigrade. It is still solid because its melting point is much higher, 1500 degrees. The microscope shows that the steel, like the rock, is made of intergrown crystals. Now we'll raise the temperature of the steel, but keep it well below its melting point. Even though the steel is still solid, some of its atoms must be moving about because the crystals are growing larger. So, under certain conditions, atoms can move in a solid and cause crystals to grow. Where in nature do conditions exist that would allow the atoms in a solid rock to move, causing the crystals in it to grow? You recall that plutonic rock is formed when a large mass of rock melts deep underground and slowly crystallizes. The surrounding rock, subjected to almost the same high temperature and pressure, did not melt. When such rock is pushed up and uncovered, we can see what the heat and pressure did to it. Most of the mountain in the foreground is made of light-colored plutonic rock we know was once molten. The dark rock in contact with it is a remnant of the surrounding rock that did not melt. Let's take a closer look at such a contact. Here we can see places where the molten rock forced its way into a crack in the darker rock, further proof that the dark rock did not melt. Here is another mass of plutonic rock. Again, we find a different kind of rock in contact with it. The darker rock is composed of distinct layers, and the layers are composed of intergrown crystals. Rocks made in this way take many different forms. Although they never melted, the heat and pressure deep underground bent and squeezed them and caused the crystals in them to grow together. So a metamorphic rock means a changed rock. Now we know that rocks contain clues to their origin. By interpreting the clues, we are able to tell how the rocks were made. This is the canyon where we found the three rocks we studied. All of the boulders here came from rocks that originated miles underground. After a long history, they are now embedded in another rock at the Earth's surface. But is this the end of the story? What would happen to this whole mass of rock if it were to be buried under miles of new layers of rock? Here is a piece of such a rock before anything like that has happened to it. After being buried miles underground for millions of years, the rock would look something like this, completely crystallized and much harder. If the rock had been carried even deeper underground, where the heat and pressure are still higher, it might look like this. How has it changed? What might have happened to this rock if it had been carried still deeper underground, where heat and pressure become even more extreme? It has been said that most rocks are made of other rocks. Do you see why?